welcome to these lectures on the topic of memory. So in today's lecture we're going to address memory, and specifically the ability to retain and manipulate information over just a very brief, short period of time, so what's referred to as short-term memory. We're going to consider some of the basics around the capacity of memory, the role of acoustic rehearsal, the serial position effect, and how long can we actually hold things in a short-term memory store for. And we're then going to consider some different cognitive models of short-term memory. So we've got one that gives a kind of traditional multi-store, multi-stage model of memory, and then a more contemporary approach that considers both the storage and processes of short-term memory. In the taxonomy of memory, it turns out that we have multiple different stores for different types of information. So the very earliest stages, we have these sensory stores or sensory registers, and these are essentially kind of like a modality specific store that can hold lots of information, but only very briefly. So less than sort of 1 second or maximum 2 seconds. So that can encode and hold information that comes in from vision, from auditory, from touch, haptic sensations. And you can think of this like a sort of really rapidly decaying or fading photograph of your current sensory experience. And anything that isn't attended to or processed rapidly decays and disappears from our awareness at this stage. What's going to be the focus of today's video is the second stage, where we have a kind of short-term and working memory store. So this is where we hold information still very briefly, so it's within a matter of seconds, sort of 30 seconds or so, with a limited capacity as to what can be stored here. And then we have a long-term memory store that's essentially unlimited in its capacity, and most of the time, once memories are robustly encoded here, then we can store these memories for an indefinite amount of time. These long-term memories can be further distinguished or broken down for non-declarative memories, which you can generally think of as things that we don't have any explicit conscious awareness of. So our knowledge of how do I ride a bike, how do I play the piano, etc. We've generally encoded those sort of procedural memories and skill-based knowledge. So these are the things that we automatically access. But then we have long-term declarative memories, and this is basically your kind of general knowledge or semantic memory. Includes episodic memories as well, so your memory for events that have occurred in the past, also your knowledge that this is a mouse, etc. So short-term memory is going to be the focus of today's lecture, and essentially reflects the capacity for holding a small amount of information in mind in an active, readily available state for this short period. So for example, if you imagine that you're going out to a restaurant, you're eating a meal, you're maybe getting a few drinks with your friends, and then the bill comes and it's 1,800. And you probably have no problem remembering and storing, if somebody says the bill is 1,800, you can hold that in mind for certainly a brief period of time. We also then have what's known as working memory. And according to this working memory model, which we'll come to later, we also have separate systems that allow us to actually manipulate and do stuff with the contents of short-term memory. So for example, if you're in this restaurant and you know that there's 6 of you and you've got to split that bill, working memory would reflect this ability to run some calculations on this. So we could divide it by 6 and know that your share of the bill is 300. It will also allow you to kind of manipulate the contents of working out how much you actually spent on your portion of the order and seeing if it seems a fair share or not. Often the case. But first, let's begin by thinking about the capacity of short-term memory. So how many things can we actually store and throw into there? And when we're working out the capacity, this is often assessed and referred to as somebody's digit span. So we can think of this as being equivalent to short-term memory as some sort of store or box that holds information briefly, and we're just asking the question, how much is it that's possible to keep in this box? Now, one of the ways you can formally test the capacity of short-term memory is using something known as a digit span test. So a digit span test will involve presenting a random sequence of numbers and seeing how many people can successfully recall. And then a determination of the person's memory span is the longest list of these items, these numbers, that a person can repeat back in the correct order immediately after presentation on 50% of trials. So typically you would do this until you hit a point where you're starting to get them wrong on 50% of the time. So we can do this, we can test out. So I'm going to read out a string out loud, and when I say go, I want you to write down what that string was. So 6, 8, 2, 5. Go. If you write this down. 3, 5, 9, 7, 2, 1. Go. Okay, not too tough so far. 2, 8, 3, 7, 1, 5, 6, 9. Go. Seven, 3, 2, 4, 9, 6, 8, 5, 1. Go. You should be finding this starting to get a little bit harder by now. Okay, next one. 6, 5, 4, 7, 8, 9, 3, 2, 1, 7. Go. Let's do one last one. Oh, we missed one. 7, 2, 4, 8, 1, 3, 6, 2, 9, 4, 6. Go. Okay, so you can get a kind of feel for where you think your own personal sort of digit span would be on this. So again, in these sort of experiments, you might then, if you start to get them wrong, you kind of drop up a number, jump up a number and do one less, and until you hit this sort of threshold where it's on average only 50% of the time that you're getting them correct. So typically, using that sort of digit span test, most people can recall a maximum of about 9 numbers. And the memory span for letters is generally a little bit smaller, around 7.3 items. Now let's test your memory again on an example that involves letters. So a list of letters is going to be presented on the screen for 10 seconds. Your job is just to try and recall these. So if you're ready, I'll give you list 1. Okay, now write down as many of those letters as you can recall. Okay, I'm going to give you the second list now, if you're ready, so pay attention to the screen and look at the next one. Now pause the video and write down all of the numbers you can recall. So what do you notice about your recall for these two different lists? And if you're like most people, you should have found it much easier to recall the second list. So when investigating the capacity of short-term memory, one of the most sort of famous findings in psychology is this idea that the capacity of short-term memory is determined not by the raw number of letters or digits that you're storing, but rather by the number of meaningful chunks of information. So if the letters that are there are clearly linked together to form a meaningful chunk, so in this case FBI, CIA, KGB, or refer to sort of detective operations, then this counts as one piece of information that can be stored in short-term memory. Whereas in contrast, the letters at the top list are essentially unrelated to each other. So YSP, you're storing the Y, the S and the P as essentially separate units of information because there isn't any link or connection with these. So to repeat, it turns out that rather than the number of individual pieces, what's more important is the number of meaningful chunks. So just some sort of integrated piece of information. And George Miller, he very famously suggested that memory span is limited to this certain number of chunks, and his magic 7 plus or minus 2 was this idea that capacity of short-term memory on average is around about 7, but then the range of this is plus or minus 2, so typically we're going to be able to remember between 5 and 9 chunks of information. Now, there are some other factors that influence memory span and how many items we can actually store in short-term memory. One of these factors is the length of the word, and specifically the amount of time it takes for us to pronounce and articulate that word. So let's try another demonstration on here. So you're going to see 10 words presented one after another for 1 second each, and all I want you to do is try and recall these words in the same order as they are presented. So, ready? Okay, these words are going to appear on the screen now. Okay, if you write down those words now. Okay, and then for the next list of words. Okay, and how many of those words can you write down now? So what do we find when individuals are doing this? You should typically find that you recall more of the first list because it takes less time to pronounce these words. So on average, with this simulate 418 milliseconds for the first list, 672 milliseconds for the second list. And this is what Muller et al. Found and termed it the word length effect. So the amount that you store not only depends on the sort of chunking and how many meaningful integrated bits of information that are there, but also how long it takes you to vocalize these words. Now this word length effect also had some sort of interesting implications, that if you speak in a language that articulates and vocalizes very quickly, so Mandarin speakers generally have a longer short-term memory store than English language speakers, just because they're able to articulate or vocalize words more quickly. So most of the research has suggested that people can remember around about 7 items in memory. So we have George Miller's magic 7 plus or minus 2, and when you call anything magic, that sort of means you can't really change it, you can't really screw around with it. However, some people, most notably Nelson Cohen, have argued that short-term memory capacity is maybe actually a lot smaller than this 7. So for instance, when people are doing these tasks, what might be contributing to short-term memory is that maybe they've actually transferred some of this information to a long-term memory store through the process of rehearsing it. So if you think of the memory tasks and the list that I gave you beforehand, one of the things that you might do as you're trying to remember it is to repeat out loud those words. So you're saying like fate, cloud, blah blah blah, etc. And his argument is that when you're doing that, maybe you put it into a sort of more intermediate or long-term memory store, rather than it being in a kind of pure short-term memory store. So he was interested in trying to see what is the capacity of short-term memory if we take away this ability for rehearsal. And how might you do that? What are some suggestions for how you might prevent somebody repeating stuff? So one way to suppress rehearsal is to use a technique known as articulatory suppression. Fancy name, but basically all it means is getting them to repeat out loud a word whilst they're doing the memory task. So if you imagine trying to do the previous task, and if I told you as you're doing that, say the word bananas over and over again, that would stop you repeating in your head the different words that you're trying to remember. So you can't rehearse anything self-vocally. And when participants do that, the amount of items that they can recall does drop down quite dramatically to around about 3 chunks of information. Another way that you can test this is using something known as a running memory task. So if we're using digits here, you can present to a participant a series of a continuous stream, basically, of different numbers. And your job is to try and hold the previous numbers in mind. And then the program will stop at some point, and you've got to think backwards and recall all of the previous numbers that have been presented. And when you do that, the mean number of digits that people can recall is only around about 3.87. So much lower than the sort of magic 7 plus or minus 2. So another way to examine the capacity of short-term memory is to ask people to recall all that they can remember from a recently presented list. So we've already done a couple of these, but it's a technique that's technically known as free recall. And I really want you to play along with this next demonstration here. So I'm going to read aloud a list of words, and after I finish, what I want you to do is recall all of the words in any order. Ready? Table, cloud, book, tree, shirt, cat, light, crocodile, bench, chalk, flower, watch, bat, rug, soap, pillow. Now, pause the video. Promise me you'll do this. Pause the video and write down as many as you can recall in any order that you like. So hopefully you've paused the video, you've written down your list. Let's see how many of those you managed to get correct. So this was the list of the words: table, cloud, book, tree, shirt, cat, light, crocodile, bench, chalk, flower, watch, mat, rug, soap, pillow. Okay, now why is this interesting? Well, there's some trends that emerge when you look at the types of words that people end up recalling from this list. So researchers consistently demonstrated something known as a serial position effect for the recall in words. So we tend to have a much better recall for items that appeared at the beginning of that list and also words that appeared at the end of the list. So in the previous example I gave you 16 words. What I'm plotting on here is hypothetical data of what you might expect. On the y-axis we've got the percentage of people that have recalled the letter, and on the x-axis at the bottom we've got the serial position. So where did it appear in that list of words? So again, we had 16. I've plotted hypothetical data for a 22 word list. So the first sort of 1, 2, 3, 4 words get recalled reasonably well, and then the last from like word number 16, 17 up to the very last one. And again, majority of people are all going to remember this last word. So why does this happen? What explanation could you come up with for why you see this effect? So basically we get a primacy effect at the start where these items are argued to be rehearsed and are more likely to be stored in a kind of long-term memory store. So at the very start, as I begin to read those out, you may be repeating over in your head table, cloud, book, and then you add on the next one. And we maybe transfer that to another sort of intermediate long-term memory store. So they probably do get stored in memory. But then we also show this recency effect. So the last few items that are presented are much more likely to be recalled because these are the ones that are currently being held in short-term memory. So albeit in a relatively fragile way. Now what else might we remember from that list and why? So is there any words that you recalled that might be a little bit more surprising? So we also find the case that if we've got particularly salient words that appear in there, so ones that stand out from the rest of the list. So for example, you might have been more likely to remember the word crocodile. So this is a word that describes an animal that's maybe a little bit more vivid and exotic than the other details, which are relatively mundane words such as table, cloud, and book. So we might be much more likely to visualize the crocodile pops up in our mind as we were going through that initial memory test here. So in the last slide, I suggested that those last few words that are in the sort of serial position order are being held in a relatively kind of fragile short-term memory store. But how can we show that this is the case, that they are sort of vulnerable to forgetting? So one of the ways is we could run that free recall task. So on the figure that we've got plotted here, along the x-axis we've got the serial positioner, and along the y-axis we've got the probability of getting them correct. And we've got them now plotted for 3 different experimental conditions. So plotted using that sort of purple line. This is the same as what we did before, essentially. So you're asked to memorize the words as they're being read out, and then as soon as the word list ends, you recall them straight away. So there's no delay. And in this case, you get the recency effect, and then you also get the classic primacy effect. So you remember words at the start and the words at the end best. Now the interesting bit is what happens if you then insert a delay after the presentation of the list of words and you prevent people engaging in any rehearsal. So if you get them to do some articulatory suppression task, you've got to count backwards or read out a word. If you ask them to do this for 10 or 30 seconds, this basically abolishes that recency effect. So that's indicating that whatever was being recalled of those recent words, it was being stored in some short-term memory store that was very fragile and vulnerable to forgetting. So on the previous slide, we saw that inserting a delay of 10 to 30 seconds could sort of severely reduce the amount of those words that are being stored in short-term memory. But how long exactly can things be remembered in short-term memory? So we know it's short, but just how short is short-term memory? So one early study that tried to examine the duration of short-term memory was conducted by Pedersen, and they asked participants to remember 3 consonant trigrams. So it's basically a string of letters, and they used trigrams so that they wouldn't be easily pronounceable, so they wouldn't form a word. And they then asked participants to recall these trigrams. They were asked to recall these at intervals of 3, 6, 9, 12, 15 and 18 seconds. And they wanted to look at what was the difference in people's accuracy rate depending on the amount of time that you've got to hold these in short-term memory. Now, importantly, to avoid participants being able to keep this information alive in short-term memory, so to stop them being able to rehearse it, they asked participants to count backwards during the wait period. So let's try this. I'll flash up just one selection of consonants as a trigram, and then you've got to count backwards from 64. So if you count backwards now, you probably find it quite easy to remember this. So the trigram was GSQ. When you're given multiple trigrams and you're asked to recall them, Then the percentage of letters recalled is very good. So it's a high level accuracy after 3 seconds, but dramatically drops off. So after 6 seconds, the recall rate is around about 50%, and then it's almost nothing after 12 seconds. So I think as well, if you find that your performance was okay, again, that's because I've only given you one trial that's on there. And we find a lot of the time that participants were okay on the first couple of trials that they were doing, but then their performance also started to rapidly drop off and would match the performance that is shown on the image here. So why is it that we forget things so quickly? What was the mechanism that underpins the fact that stuff doesn't stay in short-term memory? And really there's two different sort of classes of explanation of this. First is from a kind of decay theory perspective, is the idea that our stuff that's being stored in short-term memory just simply fades away. So this memory trace that we have disintegrates or degrades over time unless it's reactivated. So unless we can rehearse, so subvocally rehearse and say that word over again, it just slowly fades out and disappears. A second class of responses is that it disappears through interference. So the idea that different memories are competing with each other to stay available within short-term memory. And as I mentioned then, there was only minimal forgetting on the first trial of the Pedersen and Pedersen task, whereas forgetting would increasingly and sort of steadily rise over 3 to 4 trials. And this seems to suggest that there's sort of interference that is occurring between the current trigrams that you're remembering and previous ones. And it's also the case that the secondary task is causing interference during this retention interval. So the secondary task that you're doing of reading out backwards in numbers, that's interfering with that existing memory.